A triangle is physically rigid. Once you connect three straight beams end to end, the interior angles are fixed. The structure becomes entirely inflexible. You cannot shift or skew a triangle without breaking the connections. This rigidity makes the shape a closed mathematical system. With three specific data points, such as the side lengths, you can determine every remaining angle, the total area, and the center of gravity. We are going to map the operating system that makes this possible. We will identify the rules of congruence and scaling, locate the internal scaffolding that balances the shape, and deploy computational engines like trigonometry to calculate missing dimensions. To do this, we will engineer the system from first principles. We will use modular logic and explicit memory anchors to ensure these geometric rules are strictly defined and easy to recall. Geometric shapes are modular engineering systems. Simple constraints build unbreakable mathematical logic. Before you can calculate a triangle, you have to prove it can exist. The first physical constraint of geometric construction is the triangle inequality theorem. The rule dictates that the sum of the two shorter sides must be strictly greater than the length of the third side. If you try to build a triangle with sides of 2, 2, and 6, the two shorter beams will simply fold flat. The structure collapses. If you need to build a structure with a perfect 90-degree corner, the constraint is the Pythagorean theorem. The square of the two shorter legs must perfectly equal the square of the longest side, the hypotenuse. To bypass the algebra, engineers use Pythagorean triples, whole numbers that naturally satisfy the equation, such as 3, 4, 5, 5, 12, 13, and 8, 15, 17. Using these verifies a right angle without calculation. The relationship between the angles and sides is governed by the hinge theorem. Think of two fixed beams connected by a hinge. As you open the hinge wider, the distance across the gap increases. If two triangles share two side lengths that are perfectly equal, the triangle with the wider included angle forces a longer opposite side. The widest angle will always sit directly across from the longest side. These baseline constraints act as the laws of physics for geometry. They prevent structural failure before you ever reach for a calculator. Once you know a triangle can exist, the next step is determining if it matches another one perfectly. In mathematics, creating an identical copy of a shape is called congruence. First is SSS. If three lengths match, angles match. Next is SAS, two sides and the included angle. You can also use ASA or AAS. Finally, the HL theorem. In right triangles, proving the hypotenuse and one leg guarantees a match. Certain combinations of data, however, fail to guarantee a clone. If you only know two sides and a non-included angle, an SSA configuration, the structure remains ambiguous. In an SSA configuration, the unanchored side can swing inward or outward, forming two entirely different shapes from the same starting data. Similarly, angle, angle, angle only ensures the shapes are proportional. One could be the size of a stamp and the other the size of a building. If your data satisfies SSS, ASS, ASA, AAS, or HL, the triangles are mathematically identical. To apply these rules in formal mathematics, we use the two-column proof. This is a framework for stacking deductive logic to reach an undeniable conclusion. A proof always starts with a given premise. From there, you build upward using structural truths. For example, if two adjoining triangles share a middle wall, you invoke the reflexive property.
The shared side is congruent to itself, giving fixed data. Immediately after proving congruence, you invoke CPCTC. Corresponding parts of congruent triangles are congruent. This states that because the triangles match, every remaining angle and side is now forced to match as well. A geometric proof extracts certainty from limited visual data. It transforms isolated structural assumptions into unassailable facts. When shapes possess the exact same internal angles but have proportionally different side lengths, they enter a state called similarity. Similarity is governed by the scale factor, denoted as K. This is the multiplier that dictates the expansion or contraction of the shape. If K equals 2, every side of the new triangle is exactly twice as long as the original. Proving similarity requires criteria like angle-angle, or AA. Because interior angles sum to 180 degrees, proving just two angles match mathematically forces the third to be identical as well. Similarity allows engineers to calculate the physical dimensions of massive, real-world structures using miniature blueprints. Internal beams stabilize geometry. The angle bisector slices a corner angle in half. The perpendicular bisector cuts a side in half at 90 degrees. A median connects a corner to the opposite side's middle. An altitude drops from a corner at 90 degrees, showing height. If you draw a line connecting the midpoints of two adjacent sides, you create a midsegment. The midsegment theorem dictates that this new beam will always be parallel to the base and exactly half of its length. When you draw all three of any specific internal line, they cross at a single dot. These intersections are called the points of concurrency. To keep these pairs straight, you can use the mnemonic, "My cat ate our apples, but I prefer blue cheese," median to centroid, altitude to orthocenter, angle bisector to incenter, and perpendicular bisector to circumcenter. These centers of concurrency represent the balancing points of the shape, proving that predictable geometric forces keep the triangle structurally sound. When visual deduction is impossible, trigonometry provides the ratios needed to calculate the dimensions of right triangles. The operations are embedded in the acronym SO, CA, TOA. Sine equals opposite over hypotenuse. Cosine equals adjacent over hypotenuse. Tangent equals opposite over adjacent. Bypass equations using special right triangles. The 45-45-90 triangle comes from splitting a square. Its legs are identical. The ratio is 1, 1, root 2. The 30-60-90 triangle comes from splitting an equilateral triangle. Its ratio is 1, root 3, 2. For irregular scaling triangles where height is unknown, Heron's formula calculates the area using only the outer side lengths. The operational steps are simple. First, calculate the semiperimeter, denoted as S, by adding all three sides and dividing by 2. Then, plug S and the three side lengths into the square root equation. With these tools, no triangle is unsolvable. If a dimension is missing, you have the means to calculate the answer. Deductive geometry is an interconnected framework. Constraints dictate the shape. Congruence rules secure the dimensions. Points of concurrency balance the mass. Mastering these foundational rules, from SSS to SOHCAHTOA to CPCTC, means you are building mathematical truth from the ground up. Master the modular components. Master the system. Verify your constraints and keep building. Euclidean geometry is a demonstration of structurally sound logic.